There's a structure in space that shouldn't exist. Not because we haven't found it. We have. Not because the data is unclear. It's quite clear. But because, according to the fundamental principles that govern how the universe organizes itself, according to the mathematical models we've built to understand cosmic structure formation, according to the rules that seem to apply everywhere else we look, this thing is too large to be real. And yet, it's there. Stretching across a staggering 1.4 billion light-years of space, the Hercules Corona Borealis Great Wall stands as the largest known structure in the observable universe. To say it's big is to miss the point entirely. It's not just big. It's an anomaly. A cosmic anomaly so profound that it challenges our most basic understanding of the universe's structure. A challenge to our physics. A puzzle that asks us to question everything we thought we knew. This isn't just about size, it's about the way the universe behaves at its most massive scales. This structure forces us to reimagine the limits of what's possible and forces us to ask uncomfortable questions about the very laws that govern the cosmos. How could something so vast even exist? Why has it taken so long for us to discover it? And perhaps most unsettling, what does its existence say about the accuracy of our theories? For the next few minutes, we'll dive deep into this structure, how it was discovered, why it's so controversial, and what it means for our understanding of the cosmos. But before we journey into this vast unknown, let me ask you a simple question. Where are you watching from right now? At what time are you hearing about this incredible discovery? There's something undeniably profound about the fact that people, scattered across the globe, at different times and in different places, are all looking up at the same universe, contemplating the same mysteries. So, let me know where you are and what time it is. I'd love to hear from you. Now, let's get back to the wall. To truly understand why the Hercules Corona Borealis Great Wall is so extraordinary, we first need to grasp the concept of scale, not just size, but the hierarchy of structures that exist in the universe. We need to take baby steps through familiar territory until we reach structures so vast that they defy human comprehension. The scale of space is something we rarely confront directly. Most people think of the Earth, and by extension, humanity, as a dominant fixture in the cosmos. Earth, at about 12,700 kilometers in diameter, seems enormous. You could circumnavigate the planet, travel from one coast to another, and spend a lifetime exploring its surface. But this, as remarkable as it is just a tiny fraction of the universe's vast expanse. Next, imagine our solar system. From the Sun to Neptune, it's a vast 4.5 billion kilometers, equivalent to about 30 astronomical units. For context, an astronomical unit, AU, is simply the distance between the Earth and the Sun, about 150 million kilometers. At the speed of our fastest spacecraft, Voyager 1, which has been traveling for nearly 50 years, it's only just exited the solar system. And while that sounds impressive, it's only about 5 times the distance from the Sun to Neptune. That's a drop in the bucket when compared to the distances we are about to discuss. The stars in our galaxy, our Milky Way, are separated by even greater distances. Our closest star, Proxima Centauri, is located 424 light-years away, or around 40 trillion kilometers. To give you a sense of just how far that is, if we could travel at the speed of Voyager 1, it would take thousands of years to reach Proxima Centauri. Think about that. Thousands of years to reach a single star in the vastness of space. But the Milky Way itself, despite housing between 100 and 400 billion stars, is only one of countless galaxies that dot the universe. It's a large structure, yes, but not nearly as vast as the space between galaxies. In fact, galaxies do not simply float around randomly. They cluster. Our Milky Way is part of a collection of around 80 galaxies, collectively known as the local group. This group spans about 10 million light-years and includes the famous Andromeda Galaxy, Triangulum Galaxy, and many smaller dwarf galaxies. These galaxies are gravitationally bound and orbit each other, a giant dance in the universe, with the eventual fate of merging into a larger galaxy in the distant future. Zooming out even further, we find the Virgo supercluster, an immense grouping of around 100 galaxy groups and clusters stretching across 110 million light-years. This structure alone contains hundreds of billions of galaxies, trillions of stars. But even superclusters are not the final step in this hierarchy. In the 1980s, astronomers began mapping the large-scale structure of the universe, a project that would reveal something utterly mind-blowing. Galaxies are not scattered randomly throughout space. They are organized. The universe has a pattern, a cosmic web. Imagine the web-like structure of a spider's web, where galaxies form long, thread-like filaments that stretch for hundreds of millions of light-years. At the intersections of these filaments, large galaxy clusters form, and in the empty spaces between these filaments are voids, vast regions nearly devoid of galaxies. These voids can span hundreds of millions of light-years. This structure, this cosmic web, is the result of billions of years of gravitational interaction, starting with minute density fluctuations in the very early universe. After the Big Bang, the universe was nearly uniform, but not perfectly so. Small variations in the density of matter existed, and gravity slowly amplified these variations, creating the massive filaments of galaxies that we see today. But, like a great puzzle, this web of galaxies has a limit. There are theoretical constraints that suggest how large structures can grow. These constraints come from the cosmological principle, a fundamental assumption in modern cosmology that states at sufficiently large scales, the universe should be homogeneous and isotropic. This means that when we look at large enough regions of space, the universe should appear roughly the same, no matter where we look. Now, we reach the point where the Hercules Corona Borealis Great Wall appears. This structure, discovered in 2013, stretches across a mind-boggling 1.4 billion light-years. It directly challenges the cosmological principle. According to the rules we've built to understand cosmic structure, structures this large shouldn't exist. If you try to calculate the time it should take for gravity to pull such large structures together, it's simply too short for such a massive entity to have formed. This is where things get even more interesting. The Hercules Corona Borealis Great Wall is not just a collection of galaxies. It's a wall, a two-dimensional sheet of galaxies stretching across space. It's so large that even if you imagine the observable universe as a sphere with a 93 billion light-year diameter, this wall spans about 1.5% of that total observable universe. Its discovery, based on the analysis of gamma-ray bursts, gave astronomers a moment of realization that space is not as simple as we thought. Not only is the wall physically vast, but it also forces us to rethink how structures can form on such a grand scale. As we explore this impossible structure, it's clear that the universe continues to hold mysteries that challenge our understanding. While this discovery is fascinating, it's just the beginning of what might prove to be a longer investigation into the unknown. As we delve deeper into the Hercules Corona Borealis Great Wall, it's important to recognize that it isn't just about size or structure. It's about timing. The very existence of such a colossal formation forces us to reconsider the fundamental rules we've set for how the universe should evolve. Let's explore why this wall, this anomaly, is not just remarkable in its scale, but also in the way it pushes the boundaries of our cosmological theories. To understand this more fully, we need to revisit the principles of structure formation in the universe. We know that galaxies are formed from the accumulation of matter, primarily through gravity, and these galaxies are arranged into clusters, superclusters, and ultimately, vast cosmic walls like the one we're talking about. This process of matter clustering into galaxies began in the early universe, just after the Big Bang, but it didn't happen immediately. Matter, when the universe was young, was uniformly distributed, and gravity slowly pulled matter into clumps. But here's the crucial point. This process takes time. When the universe was only 3.8 billion years old, the conditions should have been too young for such large-scale structures to have formed. And yet, the Hercules Corona Borealis Great Wall, stretching a mind-bending 1.4 billion light-years, was already in place. It existed well before the universe had matured enough for such a formation to be theoretically possible, according to our models of structure formation. This discovery doesn't just highlight a massive structure, it challenges our understanding of how long it should take for such a structure to form. In essence, the universe's expansion and gravity are at odds in this case. Space itself is expanding, which in many ways works against the force of gravity that pulls matter together to form such structures. The expansion of space, particularly in the early universe when the expansion rate was faster, makes it even harder for gravity to pull distant galaxies together. The Hercules Corona Borealis Great Wall, stretching across 1.4 billion light-years, shouldn't have formed so quickly. The wall itself challenges the very timeline of cosmic evolution. The role of dark matter in shaping the wall. What makes this even more baffling is the role of dark matter. We know dark matter exists due to its gravitational effects on visible matter. It doesn't interact with light or normal matter directly, yet it exerts a profound influence on the formation of structures in the universe. In fact, the dark matter in the universe was already beginning to collapse into gravitationally bound structures long before normal matter did. This allowed the cosmic web, the vast network of galaxies and filaments, to start forming at a rapid pace. But while we know that dark matter played a major role in structure formation, we still don't fully understand how it works. What if the properties of dark matter were more complex than we realize? Could dark matter have played an even more significant role in the formation of this massive wall than we previously thought? The Hercules Corona Borealis Great Wall is a stark reminder that our models of dark matter and its effects on the universe's structure may still be incomplete. We've been assuming that dark matter behaves in predictable ways based on our observations and simulations. But what if it behaves differently under certain conditions or in specific regions of space? The wall could be a direct consequence of such unknowns. It's important to note that dark matter doesn't only affect gravity, it also interacts with itself in ways we don't fully understand. There are theories that propose self-interacting dark matter, meaning that dark matter particles might have forces beyond gravity that influence how they accumulate into structures. If this is the case, it would further complicate our understanding of structure formation, especially at the scale of the Hercules Corona Borealis Great Wall. The fact that we're seeing such large-scale structure early in the universe suggests that these unknown aspects of dark matter could be key to unlocking the mysteries of cosmic evolution. Understanding this dark component of the universe is a crucial step toward understanding how massive structures like the Great Wall can form at such an early stage. Gravitational waves and the formation of massive structures. The formation of such a large structure in the early universe also begs the question of whether gravitational waves played a role. While we're still early in our understanding of gravitational waves, the implications are profound. Gravitational waves are ripples in spacetime caused by extremely massive objects like black holes or neutron stars. As the universe expands and evolves, these waves carry information about the dynamics of the universe at large scales. Could gravitational waves have played a role in amplifying density fluctuations, leading to the accelerated formation of the Hercules Corona Borealis Great Wall? We know that the universe is filled with gravitational waves, but until recently, we've only detected those associated with stellar events like black hole mergers. It's possible that the early universe was filled with waves that influenced the growth of massive structures, amplifying certain density fluctuations that eventually led to the formation of galactic superstructures. The possibility that gravitational waves played a role in this massive structure's creation adds yet another layer of complexity to our understanding of the universe. This, like the role of dark matter, is still a theoretical proposition, but the fact that we're seeing such large-scale structures suggests that these subtle forces could have had a more profound influence than we currently recognize. A rarity, or just the beginning? Is the Hercules Corona Borealis Great Wall an outlier, or does it signal a shift in our understanding of the universe? The truth is, it's still too early to tell. As it stands, this wall is an anomaly, but not one that completely breaks the rules we've set for understanding cosmic structure. One wall doesn't dismantle an entire theory. It's just an oddity. However, it's one that we can't ignore. Astronomers have also observed other massive structures in the universe, albeit on a smaller scale than the Hercules Corona Borealis Great Wall. The Sloan Great Wall, discovered in 2003, spans a staggering 1.38 billion light-years and contains thousands of galaxies. While not quite as massive as the Great Wall, it pushes the limits of what we thought was possible. And in the 1980s, the discovery of the CFA2 Great Wall, spanning around 500 million light-years, shocked astronomers and forced a re-evaluation of the size of cosmic structures. As we explore these structures, we're left with more questions than answers. Are they anomalies or exceptions? Will we continue to find similar structures as our surveys become more refined? These discoveries could have far-reaching implications for the future of cosmology. In the case of the Hercules Corona Borealis Great Wall, we now have a clear, unequivocal indication that large structures can exist on a scale far beyond what we had imagined. It forces us to rethink our cosmic models, to consider alternative explanations, and to challenge our assumptions. Yet, this doesn't necessarily mean we should abandon everything we know. It means that there are nuances and complexities we've yet to uncover. The wall, while extraordinary, is part of the larger picture, a picture that, when fully understood, may reveal even bigger and more unexpected features of the cosmos. But that's a journey for another time. As we wrap up this part of the story, it's crucial to realize that the Hercules Corona Borealis Great Wall might just be the beginning of a new era in cosmological discovery, a time when the boundaries of what we thought possible are continuously stretched, and when the universe, in all its vastness, continues to surprise us. Just as we are on the cusp of fully understanding this monumental structure, it's clear that the universe still has much to reveal. The Hercules Corona Borealis Great Wall is not just a monumental structure, It's a profound challenge to our understanding of the universe. Stretching across 1.4 billion light-years, it forces us to confront questions that have been at the heart of cosmology for decades. How can something so vast exist in the universe, especially when we believed that the rules of gravity and cosmic expansion would have prevented its formation? This structure shouldn't be here, and yet it is. To understand how we came to this astonishing conclusion, we must consider the tools that allowed astronomers to uncover this massive wall. At the heart of the discovery were gamma-ray bursts, extremely powerful explosions that occur in deep space. These bursts, often caused by the collapse of massive stars into black holes or the merger of neutron stars, release unimaginable amounts of energy. Their brief flashes of gamma rays can be seen across the universe, even at distances of billions of light-years. In the case of the Hercules Corona Borealis Great Wall, these bursts provided the first clue. As astronomers analyzed the distribution of gamma-ray bursts, they noticed something unexpected: an unusually high concentration of bursts in the direction of the constellations Hercules and Corona Borealis. This was no random pattern. The bursts, powerful as they were, indicated something more, something physically significant in the region of space they came from. By measuring the redshifts of these bursts, astronomers were able to estimate their distance from Earth. This method, known as redshift measurement, helps scientists determine how far away galaxies and other cosmic objects are. The light from these gamma-ray bursts had traveled for billions of years before reaching us, allowing scientists to peer back into the past of the universe at a time when it was far younger. What they discovered was staggering. The gamma-ray bursts were not scattered randomly, as one might expect, but were concentrated in a massive, coherent region of space, a structure that stretched across 1.4 billion light-years. This wasn't just a cluster of galaxies. It was a distinct physical entity, a wall of galaxies that spanned a significant fraction of the observable universe. The discovery left astronomers grappling with a fundamental question: how could something this massive have formed so quickly in the early universe? The light from the Hercules Corona Borealis Great Wall had left its source when the universe was only about 3.8 billion years old, a fraction of its current age. The formation of such a structure, according to our understanding of cosmic evolution, simply shouldn't have been possible at that time. Gravity alone should not have been able to pull matter together across such vast distances before the universe had even matured. What makes this particularly puzzling is that the very expansion of the universe, which has been ongoing since the Big Bang, works against the force of gravity. As space itself expands, it pushes galaxies apart. The earlier the universe was in its development, the faster this expansion was, making it more difficult for gravity to overcome the expansion and pull matter together. For a structure as vast as the Great Wall to form, it would have required a considerable amount of matter to be gathered in a relatively short period of time. But the conditions were not conducive to such a rapid accumulation. To complicate matters, the universe's expansion rate itself accelerated over time, especially with the influence of dark energy. This meant that structures should have grown more slowly, and large-scale formations like the Hercules Corona Borealis Great Wall would have been even more unlikely. And yet, there it was, a vast, coherent structure where none should have been. A key piece to understanding this mystery is the role of dark matter. Dark matter, which makes up approximately 85% of all the matter in the universe, doesn't interact with light or normal matter, except through gravity. It has played a crucial role in the formation of galaxies, clusters, and other large-scale structures. The gravitational influence of dark matter is what allows galaxies to cluster together, and in regions of space where dark matter is concentrated, galaxies begin to form. But dark matter is still largely a mystery. We don't know exactly what it is or how it behaves under different conditions. One possibility is that dark matter's influence on structure formation was more pronounced than we thought. In the case of the Hercules Corona Borealis Great Wall, the role of dark matter could have been far more significant than we realize, allowing gravity to overcome the expansion of the universe and pull matter together more efficiently than our models predicted. However, this remains speculative. The real question is whether dark matter's properties could explain how such a massive structure formed so quickly. Additionally, the mechanics of structure formation could involve more complex processes than we currently understand. Theories about self-interacting dark matter, where dark matter particles interact with each other through forces other than gravity, could help explain how large-scale structures like the Great Wall could form. If dark matter behaves differently in different regions of space, or if its interactions are more complicated than previously thought, this could have far-reaching implications for our understanding of how structures form on cosmic scales. Even more intriguing is the possibility that this structure is not unique. The Hercules Corona Borealis Great Wall is currently the largest known structure in the observable universe, but its discovery raises the possibility that there are other walls, clusters, or filaments of similar scale scattered throughout the universe. If more such structures are found, it would suggest that the rules governing the formation of large-scale structures are far more flexible than our current models allow. If, however, the Great Wall remains an isolated phenomenon, it would further emphasize the anomaly of its existence. What remains certain is that the Hercules Corona Borealis Great Wall represents a significant anomaly in our understanding of the universe. If such a structure can exist, there may be more out there, waiting to be discovered. But for now, astronomers are left with the puzzle of how to reconcile this discovery with the cosmological models that have served as the foundation for modern cosmology. For now, astronomers have turned to the tools at their disposal to study this colossal structure in more detail. The expansion of space itself has made it increasingly difficult to study distant objects as galaxies recede from us, their light stretched farther as time passes. But with the advent of powerful new telescopes, astronomers are able to study these distant regions with unprecedented precision. The future holds great promise for uncovering the secrets of the Hercules Corona Borealis Great Wall. The James Webb Space Telescope, launched in 2021, is already enabling astronomers to observe distant galaxies with incredible clarity, while future ground-based surveys, like the Dark Energy Spectroscopic Instrument, will provide even more detailed measurements of the universe's structure. As these tools become more advanced, they will help clarify whether the Great Wall is a rare anomaly or part of a more fundamental shift in how we understand the universe's largest structures. As astronomers continue to explore this region, there will be more data to analyze and more questions to answer. What is the true nature of dark matter, and how does it shape the formation of massive structures? What are the fundamental forces that govern the organization of the cosmos, and how do they interact on such a large scale? These questions, and more, are what the Hercules Corona Borealis Great Wall leaves us with. It is not just an astronomical curiosity, it is a key to unlocking the deeper mysteries of the universe. The discovery of the Hercules Corona Borealis Great Wall has forced astronomers to rethink not just the nature of cosmic structures, but the very foundation of our understanding of how the universe is organized. As we've already seen, This structure challenges the cosmological principle, which states that on large scales, the universe should be homogeneous and isotropic, essentially the same no matter where we look. The Great Wall's sheer size and complexity make it a direct anomaly to this principle. But what does this really mean for cosmology, and how does it change our view of the universe? For decades, the cosmological principle has been a cornerstone of modern cosmology. It's been supported by a wide array of observations, from the uniformity of the cosmic microwave background radiation to the distribution of galaxies in the universe. The idea that the universe is largely homogeneous at large scales has been essential in forming our models of the cosmos, including theories about the evolution of galaxies, superclusters, and the overall structure of the universe. However, the Hercules Corona Borealis Great Wall is an outlier. With its staggering span of 1.4 billion light-years, it violates the cosmological principle in a way that cannot be ignored. The existence of such a structure suggests that the universe might not be as homogeneous as we once thought. It raises an important question. Is the cosmological principle fundamentally flawed, or is it merely an approximation that works in most cases but has exceptions, like the Great Wall? At the moment, the consensus is leaning toward a refined interpretation of the cosmological principle rather than a complete rejection of it. The discovery of rare, massive structures like the Great Wall doesn't necessarily invalidate our existing models of the universe. Instead, it suggests that our models may need to evolve to account for these anomalies. The universe might still be homogeneous and isotropic on the largest scales, but there may be rare exceptions, instances where the normal processes of cosmic evolution have produced much larger structures than we expect. This is not the first time that cosmology has had to confront such anomalies. In fact, the history of cosmology is filled with moments where new discoveries forced scientists to rethink established ideas. The realization that the Earth orbits the Sun, the discovery of the expanding universe, the detection of cosmic microwave background radiation, each of these milestones challenged long-standing assumptions. The Hercules Corona Borealis Great Wall is just the latest in a long line of cosmic surprises that are pushing the boundaries of our understanding. The impact of dark energy and the universe's expansion. One of the key factors complicating our understanding of the Hercules Corona Borealis Great Wall is the role of dark energy in the universe's expansion. As we know, dark energy is the mysterious force driving the accelerated expansion of the universe. This acceleration, which began about 5 billion years ago, has made it increasingly difficult for gravity to pull matter together into large-scale structures. If dark energy is causing the universe to expand at an ever-increasing rate, how could such a massive, coherent structure form in the first place? In the early universe, the expansion of space was much slower, and gravity was able to exert a stronger influence on matter. Galaxies and clusters were able to form more easily. However, as dark energy took over, the expansion rate sped up, pushing galaxies apart and making it harder for gravity to bring matter together. If we assume that dark energy was already dominant by the time the Hercules Corona Borealis Great Wall began to form, it would be difficult to explain how such a large structure could have developed. One possibility is that the formation of the Great Wall took place before dark energy began to dominate the universe's expansion. If the wall began to form at a time when the universe was younger and the effects of dark energy were weaker, then gravity may have been able to overcome the expansion of space and pull matter together into a coherent structure. This would explain why the structure is so massive and why it could have formed so early in the universe's history. However, there is also the possibility that dark energy had a more subtle effect on the formation of the wall. Perhaps dark energy didn't completely prevent gravity from forming large structures, but instead acted as a kind of cosmic counterbalance, slowing the process of structure formation. The fact that we see such a large structure in the relatively early universe could indicate that dark energy played a role in shaping its evolution in ways we don't fully understand. The role of dark matter in structure formation. Another crucial factor in the formation of large-scale cosmic structures is dark matter. Dark matter, which makes up about 85% of all the matter in the universe, has a profound effect on how galaxies and clusters of galaxies form. Although dark matter doesn't interact with light or normal matter directly, it exerts a powerful gravitational influence on the matter that does. In regions where dark matter is concentrated, galaxies tend to form. This is why the study of dark matter is so critical to understanding the cosmic web and the formation of massive structures like the Hercules Corona Borealis Great Wall. But dark matter itself is still largely a mystery. We know that it exists from its gravitational effects on visible matter, but we don't yet understand what it is made of or how it behaves in detail. Most models of dark matter assume that it is cold, meaning that it moves slowly relative to the speed of light. Cold dark matter tends to clump together easily, allowing structures to form efficiently. However, there are alternative theories about dark matter, such as warm dark matter, where the particles move faster and therefore clump less efficiently. If dark matter behaves differently than we currently understand, this could have significant implications for the formation of large-scale structures. The Hercules Corona Borealis. Great Wall might provide new clues about dark matter's role in structure formation. If the dark matter in this region behaves in unexpected ways, it could help explain why such a massive structure was able to form so quickly. Understanding how dark matter interacts with galaxies and how it affects the growth of cosmic structures is one of the key challenges for cosmologists in the coming years. The future of observational cosmology. The Hercules Corona Borealis Great Wall has forced cosmologists to confront the limits of their current models, but it has also opened up new opportunities for discovery. The existence of such a massive structure suggests that there is still much we don't know about how the universe evolves on large scales. As technology continues to improve, astronomers will be able to study distant regions of the universe with greater precision, allowing them to refine their models and explore the nature of the Great Wall in more detail. The James Webb Space Telescope, which was launched in 2021, will play a key role in this exploration. With its ability to observe distant galaxies with unprecedented clarity, the James Webb Space Telescope will help scientists study the Great Wall and other large-scale structures in ways that were previously unimaginable. By observing the properties of galaxies within the wall, scientists can learn more about how structures form on such enormous scales and what forces are at play in their creation. In addition to space-based telescopes, ground-based observatories and surveys are also playing an important role in mapping the large-scale structure of the universe. The Sloan Digital Sky Survey, for example, has already provided astronomers with detailed maps of the galaxy distribution across vast regions of space. The upcoming Dark Energy Spectroscopic Instrument, which aims to map tens of millions of galaxies, will allow scientists to study the cosmic web in greater detail than ever before. These advanced tools will help cosmologists answer some of the most pressing questions raised by the Hercules Corona Borealis Great Wall. Is this structure truly unique, Or are there other similar walls waiting to be discovered? How do dark energy and dark matter interact to shape the evolution of the universe? And, perhaps most importantly, how will these discoveries impact our understanding of the fundamental laws that govern the cosmos? New insights into the universe's evolution. The discovery of the Hercules corona borealis. Great Wall has provided us with a rare glimpse into the early universe, a time when the universe was still in its infancy, and massive structures like this one were just beginning to form. Studying this structure gives us valuable insights into the processes that led to the formation of galaxies, clusters, and superclusters. By understanding how such a massive structure could form so early, we can better understand the evolution of the universe as a whole. This discovery also has profound implications for our understanding of dark matter and dark energy. As we've seen, dark matter played a key role in the formation of this structure, and understanding its properties will be essential for refining our models of cosmic evolution. Similarly, the role of dark energy in shaping large-scale structures like the Great Wall could provide new insights into how the universe will continue to evolve in the future. As we continue to study the Hercules corona borealis Great Wall and other massive structures like it, we'll gain a deeper understanding of the forces that shape the universe and the mysteries that still lie hidden within it. But for now, the Great Wall remains an enigma, an incredible discovery that forces us to rethink everything we thought we knew about the cosmos. The discovery of the Hercules corona borealis Great Wall has forced astronomers to reevaluate not only the nature of the universe, but also the fundamental assumptions that have guided modern cosmology. As we've explored, this vast, coherent structure challenges our understanding of how the universe organizes itself on the largest scales. But the true impact of this discovery extends far beyond just one anomaly. It prompts us to ask broader questions about the limits of cosmic structures, the role of dark matter and dark energy, and whether our models of the universe's evolution need a major revision. This Great Wall of galaxies, spanning 1.4 billion light-years, forces us to consider whether such structures are isolated anomalies or part of a larger trend. If more structures like the Great Wall were to be discovered, it would suggest that our current models of cosmic evolution might be fundamentally incomplete. So far, the Great Wall stands as the largest known structure in the observable universe, and its sheer scale challenges the theoretical limits of cosmic structure. Yet, it also makes us wonder if the universe might be capable of forming even larger structures than we previously thought. Could there be more of these enormous walls hidden in the vast reaches of space, just waiting to be discovered? As we continue to map the universe, it's likely that more discoveries of large-scale structures will emerge. If that happens, it would suggest that the forces at play in cosmic evolution are even more intricate and unpredictable than we've assumed. The existence of such vast walls of galaxies, much larger than what our models predict, could point to processes that we don't yet fully understand, perhaps related to the way dark matter and dark energy interact on the grandest scales. On the other hand, if the Hercules corona borealis Great Wall remains a unique phenomenon, it would still force us to rethink the role of rare fluctuations in the universe's structure. It's possible that this wall is an exceptional outlier, a product of extremely rare conditions that allowed gravity to overcome the expansion of the universe and create a massive, coherent formation. The question would then become whether such rare occurrences are the exception or the rule in the formation of large-scale cosmic structures. As astronomers gather more data and continue to observe the farthest reaches of space, we may begin to uncover more structures of this scale. This would suggest that the universe is far more complex than we've realized, and that our current models of cosmic formation may need to be adjusted. These findings would force us to rethink how we view the universe as a whole, and might even require us to abandon the assumption that large-scale structures cannot exceed certain sizes. The fact that the Hercules Corona Borealis Great Wall was discovered through the study of gamma-ray bursts is significant in itself. These bursts, among the most energetic events in the universe, are not just a tool for mapping galaxy formation, but also a way of tracing the distribution of matter in the universe. Gamma-ray bursts provide a powerful method for identifying the locations of galaxies, especially those in more remote, earlier epochs. The fact that such an enormous structure could be discovered from the study of these bursts suggests that we are just beginning to uncover the vastness and complexity of the cosmic web. If future observations reveal more large structures like the Great Wall, it could indicate that we have underestimated the power of gravity and the role of dark matter in the formation of these massive structures. Dark matter, which makes up the majority of the universe's mass, is thought to play a crucial role in the formation of galaxies and clusters. But the exact nature of dark matter and how it contributes to the formation of these massive structures is still not fully understood. It's possible that the interactions between dark matter and normal matter, or even between different forms of dark matter, are more complex than we've realized, leading to the creation of structures much larger than we thought possible. This uncertainty about the nature of dark matter is one of the biggest challenges in modern cosmology. The fact that we can observe its gravitational effects but cannot directly detect it raises fundamental questions about how matter behaves on the largest scales. If dark matter is responsible for the creation of large structures like the Hercules Corona Borealis Great Wall, we will need to refine our understanding of how it interacts with normal matter and how it shapes the cosmic web. We may even need to reconsider the assumptions we've made about the speed at which cosmic structures can grow, especially in the early universe. The future of our understanding of large-scale cosmic structures will depend heavily on our ability to study dark matter more deeply. Until we have a better understanding of its properties and its role in the formation of structures, we will be left with more questions than answers. The Great Wall provides an important clue, but it's just one piece of a much larger puzzle that remains to be solved. As technology improves, particularly with advancements like the James Webb Space Telescope, we will be able to observe the universe with greater precision and begin to answer some of these questions. While the Hercules Corona Borealis Great Wall challenges our models of cosmology, it also highlights the potential for future discoveries that could completely change our understanding of the universe. Each new structure that is discovered in the far reaches of space will provide us with new insights into how the universe evolved and what forces are at work in shaping its large-scale structure. The next step is to continue exploring, gathering more data, and refining our models in light of these new findings. If more massive structures like the Great Wall are discovered, it could suggest that we are on the verge of a new era of cosmological exploration, one in which the limits of cosmic structure formation are pushed even further than we ever imagined. Whether this means revising our current models or developing entirely new theories, one thing is certain: the universe still has many surprises in store for us. As we continue our journey into the depths of cosmic discovery, we must keep in mind that each new anomaly, like the Hercules Corona Borealis Great Wall, is not just a challenge to our existing theories, but also an opportunity to learn more about the universe's true nature. The more we uncover, the closer we get to understanding the underlying forces that shape everything from the smallest galaxies to the largest superclusters. As the discovery of the Hercules Corona Borealis Great Wall continues to captivate the minds of astronomers and cosmologists, it also marks a turning point in how we study the universe. For decades, we've relied on a handful of tools to peer into the cosmos: telescopes, data analysis techniques, and simulations that have allowed us to map the distribution of galaxies, uncover hidden patterns, and understand the universe's evolution. But with each new discovery, like the Great Wall, the need for more advanced, more precise tools becomes ever more urgent. In the past, astronomers had to rely on limited technology to study distant regions of space. Early telescopes could only observe faint smudges of light in the night sky, providing a small glimpse of what lay beyond. But with the advent of modern observatories and space telescopes, we've entered a new era of exploration. The development of more powerful instruments has opened up new frontiers, allowing scientists to study galaxies and cosmic structures in greater detail than ever before. And as we continue to map the universe, new discoveries will only become more frequent and more profound. One of the most important advances in recent years has been the launch of the James Webb Space Telescope, JWST. This next-generation observatory, launched in 2021, represents a quantum leap in our ability to observe the universe. Unlike the Hubble Space Telescope, which primarily observes visible light, JWST is designed to detect infrared radiation. This capability allows it to peer through the dust and gas that obscure our view of distant galaxies, providing clearer images of the universe's earliest stars and galaxies. It also means that JWST can study cosmic structures that were once invisible to other telescopes. With JWST, astronomers can now observe the formation of galaxies in the very early universe, when the first stars were just beginning to form. This capability is crucial for understanding how large-scale structures like the Hercules Corona Borealis Great Wall could have formed so early in the universe's history. By studying these structures in greater detail, we can gain new insights into the role of dark matter, dark energy, and gravity in shaping the universe on the largest scales. But the JWST is not the only instrument making waves in the world of cosmology. Ground-based observatories are also playing an essential role in expanding our knowledge of the universe. The Dark Energy Spectroscopic Instrument, DESI, is one such tool that is revolutionizing our ability to map the universe. DESI is a massive, state-of-the-art survey instrument that uses thousands of fibers to observe millions of galaxies across vast distances. By measuring the redshift of galaxies in these surveys, astronomers can create the most detailed three-dimensional maps of the universe ever made. In addition to DESI, other large-scale surveys, such as the Sloan Digital Sky Survey, SDSS, continue to provide crucial data about the distribution of galaxies and the structure of the cosmos. These surveys are invaluable for identifying patterns and anomalies in the cosmic web. They allow scientists to look at large swaths of the universe at once, providing a bird's-eye view of the entire galaxy distribution. It is through these surveys that the Hercules Corona Borealis Great Wall was first discovered. By identifying an unusually high concentration of gamma-ray bursts in a specific region of the sky. The synergy between ground-based observatories like DESI and space telescopes like JWST will be essential for understanding massive structures like the Great Wall. As we combine data from these various sources, we will be able to refine our models of cosmic evolution and develop new theories about how large structures form. The combination of wide-field surveys and detailed observations of individual galaxies will allow us to study both the big picture and the fine details of the universe's evolution, uncovering new surprises along the way. The key to understanding the Great Wall and other similar structures lies in data. Lots of it. The more data we have, the more precise our models can become. As technology continues to advance, astronomers will be able to gather even more data, pushing the boundaries of our knowledge even further. The next few years promise to be a thrilling time for cosmology, with new discoveries on the horizon that will reshape our understanding of the cosmos. One of the most exciting aspects of the ongoing exploration of the universe is the increasing resolution of our observations. While earlier instruments could only give us vague glimpses of distant galaxies, the tools we now have allow us to observe individual stars and galaxies in unprecedented detail. With the ability to observe the composition, size, and movement of galaxies, we can begin to unravel the complex processes that drive the formation of structures like the Hercules Corona Borealis Great Wall. For example, astronomers can now study the chemical composition of distant galaxies. By analyzing the light from these galaxies, we can determine what elements they contain and how those elements have been altered over time. This can provide important clues about the history of these galaxies and the processes that led to their formation. We can also measure the rate of star formation in these galaxies, helping us understand how quickly structures like the Great Wall could have formed in the early universe. Additionally, these observations can give us insight into the role of black holes in shaping the universe. Many of the largest galaxies contain supermassive black holes at their centers, and these black holes can have a profound impact on the surrounding galaxies. By studying the interaction between black holes and galaxies, we can learn more about how matter is drawn together and how large structures like the Hercules Corona Borealis Great Wall form. Beyond just studying galaxies, the new data from these instruments will help us better understand the role of dark matter in cosmic structure formation. As we've discussed, dark matter plays a crucial role in the development of galaxies, clusters, and superclusters. But despite its critical influence, we still don't know exactly what dark matter is. By studying large-scale structures like the Great Wall, we can learn more about how dark matter behaves and how it interacts with ordinary matter. This will be essential for refining our models of structure formation and understanding how the universe evolved. One of the key challenges in studying structures as large as the Hercules Corona Borealis Great Wall is the vast distances involved. The Great Wall is located about 10 billion light-years away from Earth, meaning that the light we see from it today left the region when the universe was still very young. This distance makes it incredibly difficult to observe the structure in real time. However, by studying the light that has traveled for billions of years, we can gain important insights into how the universe was organized in its early stages and how it evolved over time. In the future, new technologies like gravitational wave detectors may also play a role in studying large-scale structures. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe, such as black hole mergers or the collapse of massive stars. By studying the way these waves propagate through space, astronomers can learn more about the distribution of matter in the universe and how structures like the Great Wall form. As we continue to improve our observational tools and refine our models, we will be able to explore the universe in ever greater detail. We may uncover new structures that are even more massive than the Hercules Corona Borealis Great Wall, or we may discover entirely new phenomena that challenge our current understanding. The journey of exploration is far from over, and every new discovery brings us one step closer to understanding the true nature of the universe. The road ahead is filled with excitement and potential. As we continue to map the universe, study its galaxies, and analyze its large-scale structures, we will refine our understanding of the forces that shape the cosmos. In the process, we will not only learn more about the Hercules Corona Borealis Great Wall, but also uncover new mysteries that will propel our understanding of the universe into the next era of discovery. As we come to the end of our journey into the heart of the Hercules Corona Borealis Great Wall, it's clear that this discovery is more than just an anomaly. It's a reminder of the vast complexity of the universe, a complexity that we are only beginning to understand. The Great Wall, with its staggering size and the questions it raises, forces us to confront the limitations of our current cosmological models. But more importantly, it reminds us that science is an ever-evolving journey. We are constantly learning, questioning, and refining our understanding of the cosmos. The Hercules Corona Borealis Great Wall challenges the very foundations of modern cosmology, particularly the cosmological principle, which has long been a cornerstone of our understanding of the universe. While it doesn't outright disprove this principle, it pushes the boundaries of what we thought was possible, suggesting that the universe may contain rare, large-scale fluctuations that give rise to structures far beyond the theoretical limits we once believed in. As we discussed, the discovery of such an immense, coherent structure forces us to reconsider our assumptions about the formation of cosmic structures. If something as large as the Great Wall can exist, are we missing something about the forces that govern cosmic evolution? Could the role of dark energy, dark matter, and gravity be more nuanced than we thought? These questions are still far from being answered, and new observations and advancements in technology will be necessary to further illuminate the mysteries of the universe. At the same time, we must also acknowledge the extraordinary progress we've made in our understanding of the cosmos. The tools and techniques that have enabled us to explore deep space, from the James Webb Space Telescope to ground-based observatories like Defies, have given us an unprecedented view of the universe. These tools have allowed us to map vast regions of space, uncover new structures, and study galaxies in greater detail than ever before. They will continue to be essential as we explore even more distant and more complex phenomena in the years to come. The Hercules Corona Borealis Great Wall, while incredibly surprising, is not an isolated incident. It's part of a larger process of discovery. As we continue to look deeper into space and gather more data, we will uncover more about the true nature of cosmic structures, the role of dark matter and dark energy, and the fundamental laws that shape the universe. The Great Wall may be one of the largest known structures in the observable universe, but it is far from the last mystery we will encounter. In the future, we may uncover even more massive structures, walls, clusters, and filaments of galaxies that stretch across the cosmos. We may even discover entirely new types of cosmic phenomena that challenge everything we thought we knew. The universe is vast, and it's still full of surprises, and that is what makes the pursuit of knowledge so exciting. We are living in a time when these discoveries are becoming more frequent and more profound, and each new revelation brings us one step closer to understanding the cosmic forces that shape the very fabric of reality. As we conclude this exploration, let's take a moment to reflect on the bigger picture. The Hercules Corona Borealis Great Wall is just one part of the grand cosmic tapestry, one thread among countless others. The universe is not just a collection of galaxies, stars, and black holes. It's an intricate and awe-inspiring structure, constantly evolving and full of mysteries yet to be solved. Every new discovery, every anomaly, and every question that arises only adds to the wonder and excitement of this cosmic adventure. We are not just observers in this vast universe. We are participants in its ongoing story. With every question we ask, every new piece of the puzzle we uncover, we move closer to understanding not only the universe itself, but our place within it. We may never have all the answers, but it's in the search, the constant quest for knowledge, that we find the true beauty of the cosmos. The Hercules corona borealis. Great Wall serves as a reminder that the universe is vast and full of unexpected wonders. It challenges our understanding, pushes the boundaries of science, and humbles us with its complexity. But it also inspires us to keep looking, to keep questioning, and to keep discovering. Thank you for joining me on this journey through one of the most fascinating and mysterious structures in the universe. As we continue to explore the cosmos, there will be more questions, more discoveries, and more surprises waiting for us. The universe is calling, and it's up to us to answer. Stay curious, keep exploring, and never stop asking the big questions. The adventure is just beginning. This is the end of our exploration of the Hercules corona borealis Great Wall, but the story of the universe is far from over. Keep your eyes on the stars, and who knows what wonders we'll discover next. Until then, stay tuned for more cosmic discoveries. The universe is vast, and we are only scratching the surface.